We are now familiar with analysis of circuits containing one port nonlinear elements, that is a two terminal nonlinear element like a diode. When we want to make something like an amplifier, it is preferable to have two ports, one port to feed the input and another one to take the output from. So, we will look at two port nonlinearities, and the basic principle is exactly the same as what we did for single port nonlinearities, just a minor extension, and it could be further extended to higher number of ports. Okay. For simplicity, I will consider three terminal two ports, that is, there is a terminal which is common to the two sides. This is port 1 and that is port 2. Okay. So, it is denoted like that. So, this common means that it is common to the two sides. Now, as usual, we define the voltages and currents as per the passive sign convention. Because it is a two port, we have two voltages V1 and V2 and currents in this direction I1 and I2. And just for comparison, I will show the single port or a two terminal nonlinearity here. We have a single voltage and a current. Now, in case of a single port or a two terminal nonlinearity, we could define I as a function of voltage. Okay. Of course, we can also do the other way around, define the voltage V as a function of current, but we choose this representation. And in this case, we will say that I1 is some function of both V1 and V2. All it says is that the current going into this depends on both V1 and V2, that is all. And similarly, I2 is another function, in general a different one, of V1 and V2. Okay. And by Kirchhoff's current law around this entire element, we know that the current coming out of this has to be equal to I1 plus I2. Okay. Again, many other possibilities exist. We could define the voltages as functions of currents, or this voltage as a function of this current and that voltage, and so on. Okay. You are familiar with linear two ports and all the possible two port parameters which can be used to describe them. Exactly the same thing can be done for nonlinear two ports. The relationships will now be nonlinear, that is all. Okay. So, all the choices of dependent and independent variables you saw earlier can also be used here. We will use currents as functions of voltages, because for the devices that we have now, this is the most relevant representation. Okay. So, that is the representation of a two port nonlinear element, two port nonlinearity. Now, for a single port nonlinearity, we could give this expression. We could also draw a graph, I versus V, and for the particular example of the diode, it happened to be like that, although we can have anything that we want. We can make a similar graphical representation for the two port. Okay. Now, first of all, we have two quantities here, I1 and I2, and we have to draw graphs for both of them. Now, I1 is a function of two variables V1 and V2, and you can imagine a three-dimensional graph, that is, you have I1 as a function of V1 and V2, which are two dimensions by themselves. Okay. Basically a 3D plot, but such a plot is very hard to read and interpret. So, normally what you do is instead draw a number of two-dimensional graphs. That is, we plot I1 versus V1 with V2 being constant, and you must be familiar with this. In this case, V2 is called the parameter, and it can be anything. Okay, I will just show some arbitrary example. I1 versus V1 could be something like that. For a particular value of V2, for another value of V2 it could be like that, and so on. Okay. So, basically plot I1 versus V1 keeping V2 constant. So, that is a two dimensional plot, okay, one variable versus another variable, and then vary V2 and repeat the plot. So, basically you get a family of curves, okay, and exactly the same thing can be done, and clearly you can see that there are four possible plots: I1 versus V1 with V2 being constant, I1 versus V2 with V1 being constant, similarly I2 versus V1 with V2 being constant, and I2 versus V2 with V1 being constant. Okay. So, we will have I1 versus V1, I1 versus V2, I2 versus V1, and I2 versus V2. Okay. And they could be anything. I will just show some representative examples. So, in this plot for instance, V2 is the parameter. So, what it means is, for each of these curves V2 is a constant, and for different curves we choose different constant values of V2. Okay. And similarly, for this one we will have V1 as a parameter, and it could be anything. Okay. It could be something like that. Okay. And similarly, I2 versus V1 could be something like that, and I2 versus V2 could be something like that. Okay. So, V2 is a parameter in these two plots, and V1 is a parameter in those two plots. Okay. So, this is how we can graphically show the relationships, the current voltage relationships of a nonlinear 2-port or any 2-port. We can also do it for a linear 2-port. In case of a linear 2-port, these curves will be straight lines. That is all. Okay. This is just like the IV characteristic of a resistor, which will be a straight line. IV relationships of 2-port will also consist of 4 plots, but all plots will consist of straight lines. Okay. Now, when you have a nonlinear 2-port embedded in a circuit, you have to write the circuit equations, and you will have nonlinear equations because of the nonlinear nature of the 2-port, and then you have to solve the nonlinear equation numerically. This is what we will have to do in order to solve for the operating point. Now, right now we have not considered any specific nonlinearity, but a general one in the form of F1 and F2. But you know that given the nature of the nonlinearity, given the definition of F1 and F2, you can solve the nonlinear equation. Okay. So, we will not deal with that aspect any further here. We will assume that you will be able to solve for the operating point. What we are more interested in is in the incremental analysis when you have a nonlinear 2-port. Okay. Because when we vary the signal, when we vary the voltages or currents in a circuit, okay, what happens is we treat them as increments over the operating point. In order to do that, we have to be able to do incremental analysis of nonlinear circuits. Okay. And it is only in the incremental sense that a nonlinear device will have power gain. Okay.